Okay, so we are now into second lecture, and today we will start with solidification. So as I said, in this particular course we are covering solidification and powder processing. So this is the solidification part. What is solidification, or basically why is, let's start with why is science of solidification so important. Solidification is applied to a wide variety of materials, from metals and alloys to ceramics and to polymers. Although we will be here concentrating only on crystallography or crystalline materials, for example metals, alloys and ceramics, not the polymer part, but the solidification can also be used for polymers as well as glasses. Solidification is of such importance simply because one of its major practical applications, which is casting, is a very economical method of forming components. Now you would have seen the metal, so many metal components or metal parts in your home. Now at some stage that particular metal component must have been in a molten stage, it must have been in a billet form after that, and then given different shapes. It may become the fan blade, or it may become automobile component, and so on and so forth. Now properties of casting is not so easy to control, okay, hence understanding the science behind it is important. And so this is another very important reason why we must understand the science, because you cannot easily manipulate the casting process, and only if you understand the science that you will be able to manipulate the process and hence be able to achieve desired results. Now the fourth point I have already made, manufacture of every man-made object involves solidification at some stage, and hence it is economical and relatively easier to achieve desired characteristics of the component by controlling process at solidification stage itself. For example, let us consider macro segregation. Macro segregation is a problem in casting which cannot be gotten rid of in later stages during any other kind of forming process, whether you are doing metal forming or whether you are doing powder processing. Macro segregation would exist. So why not control this macro segregation in the casting, in the solidification stage itself, by controlling the parameters, and that will be possible only if you understand the science of solidification. This science of solidification is also important because it has allowed us to ensure or to make purify some metals. We would be looking at some examples where purification, or what is also called as, the process is called as zone refining, is possible because we understand the process or the fundamentals properly. Some of the important processes, let us look at some of those processes which involve solidification. Like I said, casting is one of the big classes. So you can have ingot casting, meaning just large chunk of metals being formed, or die casting where you will have a mold with a desired shape that you want to make, or it can be investment casting which is also called as lost wax casting, and then there are something called as continuous casting. We will look at one slide for each of these. Another important place where solidification is used is joining. So like I said, one of the example was welding. Another is welding involves melting of the base metal as well as the filler metal. Another joining process which does not involve melting of the base metal but only of the filler metal are soldering and brazing. So these are also joining process. Soldering, you would know, is used in electronic components. Brazing you would see in the small components where you have metals which have for joining metals which do not have very high melting point. Other than that, there are some exotic, let us say exotic processes, for example melt spinning, planar flow casting, atomization, which is used for making powder particles for powder processing, surface remelting to get some special properties at the surface. Then you have the directional solidification which I was talking about, which we use in turbine blades to make single crystals, or for making single crystals for single crystal, large chunks of single crystal silicon, which can then be cut into small thin wafers, which are then later used by electronic industry for making your smartphones, laptops or televisions, etc. So let us again come back to the some of the pictures that we saw earlier. So in order to understand or appreciate solidification, let us look at two processes, casting and welding. Now I said earlier also that casting we use in decoration form, in the art form, as well as for utility form. And again I have shown you some of the pictures over here. The two top ones are the Dokra art forms, which is from the Indian culture. Actually you would be glad to know that in India we had this technology or this knowledge 4000 years back, and people were using this Dokra art form, which is nothing but lost wax form, for making sculptures like this. And even today I showed you the example of Moradabad, where the sculptures are formed. Moradabad, which is also called as the Pital Nagari, or the land of brass, because a lot of brass sculptures were made there, and now people are, because of the rising cost of brass, people have now slowly and steadily changing to aluminum alloys, and that has again been possible only because you understand fluidity. For example, this why were we using brass? Because brass has very good fluidity. Now how to get good fluidity in aluminum alloys, which is cheaper? If you know that, then you would it will be desirable to switch to such materials, because it will reduce the cost. And these are again the utility things, manifolds and turbine blades. Now let us look at the definition of casting. Casting is a process in which molten metal flows by gravity or other force into the mold, where it solidifies in the shape of mold cavity. You will have a mold cavity, and you pour in the liquid metal and it freezes there. So there are basically 3 steps involved: melt the metal, pour it into a mold, allow it to freeze, and then you get the final component or decorative form, whatever you were planning to get. Now this casting, like I said, is one of the most widely used technique which comes under solidification. So there must be some large scale advantages of it, and it can create complex part geometries. In solidification you can get very complex shapes, 3D shapes. You can create both internal and external shapes. For example, I was talking about undercut shapes. Those undercut shapes are also possible by using casting, and both solid as well as large hollow shapes. You can get near net sub process for small to large components for both ferrous and non-ferrous materials. So it is not that casting is only limited for ferrous metals, which is actually a very big class of metals. You can also get non-ferrous metals, and we have already seen the example, the brass and the aluminum alloys. Another thing is that it is relatively quick, and mass production can be done with very low scrap. So you can, because whatever scrap is there, you can put it back into the melt, and then you get back, or you are able to reutilize it, and you can very quickly get, all you need is basically, let us say, wooden pattern. And if you have a wooden pattern, you would as I will show you in the next slide, you can make the mold around it, and in that mold you can get the desired shape. So all you need to do is make a wooden pattern for whatever shape that you wanted to, or that you desired to make. So it is relatively quick, and depending on what technique you can what technique you are using, you can get very good surface finish. Let me caution you here, when I say good surface finish, it is not always that in casting you can get a good surface finish. It will depend on what particular casting process you are using. Now there are also some disadvantages for casting. One of them is mechanical strength is poor. Why is the mechanical strength poor? Because the microstructures that form are very inhomogeneous. Near the surface, like even in the first example that I showed you, near the surface you get chilled zone, and inside you get some columnar zones, and therefore the microstructure is not so homogeneous, and so you get not so good strength. And like I said, surface finish is also a disadvantage, because in most of the basic casting techniques like the sand mold casting, you will require some amount of surface finish to be able to use it as a component. So casting is again very large class of manufacturing technique. What are the specific casting techniques? Sand casting is one of the most commonly used. In fact, if you know that the engine blocks in automobiles are made by sand casting. So sand casting composes 60% of all the casting that is done. Then there are some other techniques like investment casting, die casting, permanent mold casting, centrifugal casting, and shell mold casting. So those were the different specific examples of casting, but we can also classify casting on a different type, or basically on what kind of mold and pattern you are using. So in that way we have 3 different classes of casting. One is expandable mold permanent pattern casting. In here what you have, that the pattern is permanent, that is it is not being made again and again, you just use the same pattern and keep using it again and again, not have to make it again and again. But the mold part, which is the surrounding part, that is expendable. So if, for example, in the most common example is the sand casting. You take a wooden pattern, make the sand mold around it, and then pour the liquid metal inside it, then break it, you have a component. Then again you use the same wooden pattern, put the sand mold around it, and you have another component, and so on. Advantage is that you can get very complex shapes using this technique, and the disadvantage is that production rate is limited because you have to make the mold again and again. Another example, another class of casting is expendable mold, expendable pattern. So here the pattern is also expendable, not only the mold also, in the previous example you saw the mold was being broken, but here even the pattern is being broken. And one of the most common example is investment casting. So you take a pattern, for example you make it from a wax, then you coat it with a slurry or a ceramic which is very hard, and then you melt the wax out of it so that the wax comes out, so the pattern is gone, and then you pour the metal inside it. Now the metal has taken the shape, the cavity shape, but then you break that the slurry that or the ceramic mold that was around it, so the mold is also gone and the pattern is also gone. So this is a expendable mold, expendable pattern process. And the third one is permanent mold process. So in this process you wouldn't even need a pattern per se, you have a permanent mold, whatever shape that you wanted to get you will have to use that, and you can pour the liquid metal directly, again take out the component, again pour the liquid metal into it, and so you can get several of these components at a very fast rate. So yes, that is the advantage, higher production rate. But again the disadvantage is what, since you have the permanent shape, you will be limited by geometries, you cannot get any kind of geometry. So the geometry is limited and it needs to be an open mold, so that you can open it easily when the casting is completed. So here is a detailed drawing of sand casting. Over here what you see is there are two parts of the flask. On the outside what you see as this grey region, this is a flask. On the top flask is called a cope and the bottom flask is called the drag. Now in this orange region that you see is the hollow part where the liquid metal will get into, and this is up to this part is your component that you want to make. And you also see there is some sand component is put in there, it is called core, meaning for example the component that you want it to be hollow over here. So you put a core in here, the core is also made out of nothing but sand, but this is a different kind of sand which is a little harder. We will look at some of the properties over there in in one of the slides. And to ensure that it remains in place, because the liquid metal may be flowing at very large speed over there and it has very large buoyancy, you put in some chaplets which ensures that this core remains in its place. And then there is a pouring cup from which you pour the liquid, and then there are open riser from which the liquid will come out, otherwise the gases or the air has to come out. So that is the open riser. Apart from that you also have what is called as a blind riser, to ensure that whatever you say light impurities that may be there in the liquid metal, they will get trapped into this. So this is called a blind riser, and this is an important part of the design if you need to have good purity of the material. So this is a simple way to understand sand casting, and so what you look at in the brown parts are actually the sand part, and you put that sand part around the pattern and hammer it to ensure that the pattern takes the shape, or the sand takes the shape around the pattern. And once the pattern has been formed into the sand, you take away the two flasks, the bottom part and the top flask, and then take out the pattern slowly from inside. And once the pattern has been taken out, there will be a hollow region, and then you put the bottom flask and the top flask on top of it, and into that when you put that together you would be able to pour the liquid metal into it. So here through using this pouring cup, and this liquid will go into the sprue. Now if you understand the science of casting, you would be able to understand that why there is a taper in this sprue. It cannot be a parallel kind of shape for this taper. It cannot be a parallel cylinder. There is a taper here and there is a reason for it. We will look at that later on. So again let us look at some examples of the sand casting. So here is an example. So here is the components or the shape, not the components, sorry, the shapes that have been, or the pattern which needs to be formed. So you see there is a hollow region here and there is a sand, like I said, this is a core, and these cores are kept here in horizontal, these two cores, and there is a vertical core over there, and this is the drag part, this is the cope part. You put it over there and the pattern has already been taken out from it. So you put it back and then you pour the liquid in it, and the liquid will go inside and it will fill all those hollow regions and you will get something like this. So this is the component, or this is the 4 components put together along with the sprue and the pouring basin, you can see over here, and when you cut it off, when you separate it off, you will get these 4 components casting which is obtained from the above mold. Now sand casting, like I said, is a very commonly used method, so there must be some advantages to it. So let us quickly take a look at some of the advantages that we have in sand casting. It is relatively cheap, it is sufficiently refractory even for steel foundry use. So sand, since sand has such a high melting point, you can use it as a refractory even for melting of steel. So this is another very big advantage for sand casting. So even a very high melting material like steel can be easily melted and given shapes using sand casting. But it is not that sand casting has only advantages, it also has some disadvantages. It has various heat treatments may have to be applied to relieve stresses from the initial cooling and to add hardness. Once you do sand casting, because of the stresses that are generated onto the surface, you may have to apply some additional heat treatments after the casting process is done, so that the stresses are relieved. If you do not release the stresses, then the component may have very poor properties, especially the mechanical properties may become very poor. So additional heat treatments may be required whenever you are doing sand casting. When we are doing casting, another disadvantage is when we are doing casting with metals like iron or lead, which are very heavy metals, then on top of the cope you need to put in some heavy material or heavy weight. Why is that? Because the buoyancy of these metals may cause the cope or the top part of the mold to start floating, and therefore this kind of problem is called as floating mold. And to get rid of this, you must put some heavy weight onto this sand casting. So let us, since we are looking at casting as one of the important applications of solidification, and sand casting is a very commonly used casting technique. So let us look at casting in a little bit, particularly the sand casting, in a little bit more detail, so that we can understand and appreciate what is going on when we understand, or when we try to understand the science behind it. So there is a pattern over here. Now you can make these patterns, for example, by simple 2 wooden blocks. It can be in a single piece or it can be split, or you can have a matching plate like the matching plate is seen over here. You put the 2 parts together and then put the sand around it, it will allow it to take the shape and then take away the pattern out of it to create the hollow region where you will pour the liquid. So this is the pattern and the purpose of the pattern. Then there are also cores in sand mold, and again let me bring back the picture that we showed you earlier. So there is a core over here because you wanted a hollow region. So the purpose of the core is to allow formation of hollow regions inside your surface. Now again like I said, this is also formed of sand, but it has certain different properties from the sand that you are using for the mold purpose. What is different? It must possess strength. You see this is held over here, but it is still not breaking. So this must be very high strength, and it is obtained. How do you obtain this strength? You put it in the furnace, you make this desired shape, desired hollow core shape, and then put it in the furnace to make it hard. Then it must have permeability. Now when the liquid metal flows into it, a lot of gases would evolve. Now those gases may also get into this core region. Now the core region must have permeability to allow those gases to escape through it. If not, then again the core may break. Another is thermal stability, because we are talking about liquid metal temperature which is of the order of 1200 or 1500. So that the core must be able to retain strength even at those temperatures. So thermal stability must be there. And finally collapsibility. So it may look like collapsibility is inverse of strength, but it is not really. Collapsibility you need, because at the end when you have done all the, when you have made the component using casting, you want to reuse the sand, you want to break it and then reuse it. So it should also have collapsibility along with the strength. These cores, like I said, can be anchored by core prints or chaplets to ensure that buoyancy of the liquid does not displace it from its place. Now the sand mold casting, when we are talking about, we should also understand that the sand is not just any sand. There is, the sand that is used has to have certain characteristics. For example, what is most commonly used is green sand, because we are adding some moisture to a mixture of sand grains, clay and water. Each of these have some purpose. For example, sand grain, that will form the basic building block, while clay and water or the moisture will form the glue. So it holds the particles together. Other kind of sands use different kind of binders. For example, in the green sand that I talked about, clay is the binder, water and clay are together forming the binder. So this is the most general one. Other binders that you may have in different kinds of sand include organic resin or inorganic binder, for example sodium silicate and phosphate. So based on it we can have different kinds of sand mold. Green sand mold, the one which is which has moisture. So since it has moisture, it is called green sand mold. Then there is dry sand mold, where you, since you do not have moisture, you add something else, for example organic binders rather than clay and water. Then there are skin dried mold, where the mold cavity surface of green sand mold is heated to form a strong layer up to a thickness of 10 to 25 millimeter. So that is the expandable mold process. We can also have an expandable pattern process, like I said earlier, and in this, for example, this is the picture which explains what is the expandable pattern process. There is of course some advantages for it as well as disadvantages for it. Here we have a mold wall. Inside it you will make a polystyrene or a foam pattern, and you will spray it with some refractory material so that the surface finish comes out good, and then put the sand around it so that the sand takes again the shape around it. Now instead of taking this polystyrene foam out of the mold, as we did in the case of sand mold casting using wooden pattern, here we can directly pour the liquid metal into it. Why? Because this polystyrene foam can very easily melt and escape. So when we pour the liquid metal, this polystyrene foam will melt and it will escape from here and creates the vacuum space or the hollow space that is needed to fill the liquid metal, and therefore this process will be called expandable pattern process. Advantages is that you do not have to design your pattern, and there will be no parting lines. Most of the time you will have when you have pattern, it will be of two different components, two different parts, so there will be a parting line, and you will have to design the patterns accordingly to ensure that the parting line is minimum and it is not obstructing with taking it out. So those kind of things you do not have to consider over here. Pattern need not be removed, so there will not be any breakage while removing the pattern, but the disadvantage is that every time you will need a new pattern. Another example of casting which we described earlier was permanent mold casting. So we had expandable mold casting with permanent pattern, expandable mold, expandable pattern, and then permanent mold casting. So this is the third class of casting that we talked about earlier. In here we have something like this. This is the mold. So these are the two pieces of the mold, as you can see, and when you put them together there will be a hollow region. This is the hollow region, and if you want to put a core, you can also have a rod in over here along with, or even have a sand core for that matter, and then pour the liquid metal. Now when you separate the two pieces of the die, you will have the required shape. So this is the required shape that you can get. Now as you can see, the mold has not been damaged and it remains as it is. The pattern was formed using the mold, so you do not need a pattern, and therefore this is a permanent mold casting without any requirement for pattern. Advantage, since this permanent molds are made out of metals, so one of the biggest advantage here is you get good surface finish. You do not need to do any final finish to give a good to ensure fine surface finish. You get fine grains because the heat conductivity is very high, so you can get very fast cooling rate giving very good strength, and you can also get very good dimensional control. Disadvantage is that you will have to have, you can only have single geometry. Now this particular die cannot be used for any other purpose, you can only have this particular shape, you cannot make any other shape. So this is used only for low melting metal alloys. If you for this like I said, these dies are made of some metals and those metals are usually steel. So if the melting point of the metal comes very close to steel, you would not be able to put or pour it into it. So the material or metals that can be used are only those which have very low melting points with respect to the die material, and this is only suitable for high volume production. As you can see, you have made a permanent die, so you must have invested a lot, so you will be able to use it only for very large volume production purposes. So the examples are, there are lots of examples in the automotive industries, for example automotive pistons and pump bodies which are regularly manufactured using these permanent mold casting technique. So we will end over here, and next time we will look at some more casting techniques along with the welding that we talked about with some of, and also give you a layout that we are going to cover for solidification. Thank you.